Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, I'll go through this AQA topical A Level series. This is specifically on nucleophilic substitution mechanism. It's one of the case study mechanism under haloalkane or halogenoalkane chemistry. So in this first question, we have a multiple choice question. We have a pentane nitrile. A nitrile basically is a carbon triple bond organic compound there. Pentane is 5 carbons. So if I draw skeletal formula, so let's say this is the CN, triple bond between the carbon and the nitrogen. This is the highest priority carbon, the most important carbon. The rest are just alkanes, which you don't consider a functional group because alkane is present as the most fundamental kind of well, the groups, I guess. So there's 1, 2, 3, 4. There's butane nitrile. You want pentane nitrile. So you can react it with 1 bromobutane. So how in the world do you do this, yeah? So you started with 1 bromobutane, 1, 2, 3, 4. You're adding carbon because you started with 4 carbons and then you want to end up with 5 carbons. So you will use a CN minus. You cannot use a HCN molecule. So if you use a HCN molecule, this is just delta plus delta minus. This is a weak nucleophile as it is not a strong nucleophile because it's not a fully charged ion. This is a full ion from, for example, KCN or NaCN in ethanol. So that is going to be your nucleophilic substitution where there is a delta plus and a delta minus. So the lone pair attacks the carbon with the delta plus. That's your first step. And then you will have the second step where you will break the CBr bond. We don't usually label the first step and the second step. I've just put it there so they can see what is going on there. So option D is the answer there. Question number 2, we want to get ethyl amine. So ethyl there is 2 carbons and we have an amine which is basically RNH2. The nitrogen there still has the lone pair there. So you will see that you require 2 ammonia molecules because the first ammonia molecule is acting as a nucleophile. So that is your first step. Nucleophile attacks the carbon delta plus, and your second step breaks the carbon Br bond. You're going to get a nitrogen with a positive charge because the nitrogen now form a dative or a coordinate covalent bond to this carbon center. It has a positive charge of the carbon, and then this is the second ammonia molecule which is no longer acting as a nucleophile. This one acts as a base. What is a base? A base dissociates water to give you OH minus. A base accept H plus is a proton acceptor. You will have learned this under definitions of acid and bases, whereas this one, the first NH3 as a nucleophile because this is after all a nucleophilic substitution mechanism. So which of the curly arrow is not correct? The NH3 wants to accept the H plus, so the wrong one will be this one here because it should be from the 2 electrons in the covalent bond, you will go back to the nitrogen. So from the covalent bond back to the nitrogen such that you will get CH3, CH2, and H2 like this. Trigonal pyramidal with 3 bond pair and 1 lone pair, 107 degree. So curly arrow number 4 is actually the mistake there. Question number 3, we have a method that is used to prepare ethyl amine. So pretty much the exact same question as the previous thing. The ammonia, the first ammonia, acts as a nucleophile. A species which is electron rich must have lone pair. This one was wrong just now. It would have to be that, going back to the nitrogen, giving back the lone pair to the nitrogen. So this one is as a base. So which one about the reaction is not correct? Ethyl amine is a primary amine. So yes, because you have CH3, CH2, and then NH2. So the nitrogen of the amine is bonded to 1 carbon. So it is primary amine, so not that. The mechanism is a nucleophilic substitution, so that is definite. Hang on. What do they want? This is a negative question, not correct. So this is correct. This next one is also correct, because it is a nucleophilic substitution. So that is not what we want. That's not what we want there. Using an excess of bromoethane will prevent further reaction to form a mixture amine product. It's actually not using excess of the electrophile, it's using excess of the nucleophile, because you want to use concentrated ammonia so that you have a lot of ammonia, and they will not be competing with the ethyl amine, which could potentially act as a nucleophile as well. So that must be the non-correct answer. So if that is not correct, so that must be what we are looking for as per the statement, the question. Ammonium bromide, so the product you are forming will be NH4 plus and then Br minus, because that is your NH3 acting as a base except for protons. But of course you also get your ethyl amine, which is your desired product, which is a primary amine, and therefore this is true, this is correct, so it is not what we want there. Number 4, why are fluoroalkanes unreactive? So we look at things like CFCs, we cause the ozone depletion, and the reason is a result of forming free radicals. So chlorine or bromine radicals. So free radicals, species with unpaired electrons. So species with unpaired electrons, how do you form them? You form them by homolytic fission. Homolytic fission, when you split the covalent bond equally, such that one electron in the covalent bond goes to each of the atom. Here you are having chlorine radical, bromine radical. So we need to think about breaking CF bond, CCl bond, CBr bond. So of course, when you go down to group 7, the halogen, you have more filled electron shells, and you can think about the outer shell electrons, or the electrons in the covalent bond is actually further away from the nucleus. You get a longer covalent bond, and therefore these electrons they are sharing in the middle is getting further and further and even further away from the nucleus. Therefore, we think about this being a weaker covalent bond. So in hindsight, if you look at that, so we can think of CF bond being very strong, and therefore it's more difficult to break. It requires a large amount of energy to break in order to form the fluorine radical, and therefore the CF bond doesn't break easily, therefore it's fairly unreactive halogenoalkane. Question number 5 is a synthesis question already. So if I start to convert this into skeletal, it's a lot easier to follow in skeletal if you know what I'm saying. It might look tricky, but skeletal is actually the best and the simplest way of following organic chemistry. The carbon forms 4 covalent bonds, 1, 2, 3, 4. This is a central carbon. We don't show the hydrogen bonded to the carbon in a skeletal formula. So this carbon forms 1 covalent bond. There is 3 hydrogen, 3 hydrogen, 3 hydrogen. No hydrogen there because 1, 2, 3, 4 covalent bond already. Carbon forms 4 covalent bond. 1, 2, 3 are shown. There's 1 hydrogen there. There's that. Carbon forms 4 covalent bond. 1, 2. So there is 2 hydrogen there. There's the CH2. The most important functional group there is your alkene. So we think about alkene chemistry. I draw the product Q. So the CH3 3 times is the same. Now I have a CHCl and I have a CH3. Carbon forms 4 covalent bond, 1, 2, 3 hydrogen. There should be 1 hydrogen only. So the other one is going to be Cl like this because there is 1 hydrogen there. Next up, if you look at the formation of R, it's actually going to look pretty similar to Q, except that I have replaced the Cl with NH2, which is the amine group there. And the nitrogen of the amine is bonded to 1 other carbon. This is what you call a primary amine. Now give the IUPAC name for compound P. So this is P. We find the longest chain carbon. So 1, 2, 3, 4. But don't forget that when you name carbons, you also have to think about the other way around. So I've done this in black color as well. So you could do 1, 2, 3, 4 or 1, 2, 3, 4. These 3 carbons are exactly identical. But going through the black color and the pink color numbering, with the pink color, you will get 3 alkene, 3 in. With the black numbering, you'll get 1 in. You want the lowest number possible, so the pink color is not going to be good. So 4 carbons, that is but 1 in. However, I have a branch and a branch. There are 2 methyl group. They are called dimethyl. Both of them are at position 3. So it's 3, 3 dimethyl but 1 in. So you will see that I actually started naming it from the back because it's a lot easier to follow the longest chain carbon, and then think about the branches, and then think about the position of the branches. Going back to Q, it's going to be pretty similar idea. We want the lowest number possible. So I'm going to do that 1, 2, 3, 4 rather than 1, 2, 3 because 2 is smaller than 3. So we know that this is going to be butane because there is no longer double bond between the carbon-carbon. And there is a chloro. This is 2 chloro. Then your decision is, where does the chloro come in? Is it the chloro or the dimethyl first? Because your dimethyl is still at position 3, 3. If I look alphabetically, C is smaller than D, so C comes first. So 2 chloro, 3, 3 dimethyl butane, because C comes before D, so therefore I put the 2 chloro first before the dimethyl butane there. In part B, conversion of P into Q uses HCl. This is hydrogen chloride. This is not hydrochloric acid solution. Name and outlined a mechanism. It's 5 marks potentially. This one should have been having quite a bit of space for you to draw the mechanism for the 5 marks. So this is P going into Q. So P going into Q is basically the formation of the haloalkane from the alkenes. So I'm just going to add 1 page and show you. Oh, actually, there's space at the bottom. Okay, so I'm just going to draw that now. This is part B. So that is that. Going to Q. So that is going to Q. Okay, I think it might be best if I start on a new page actually, because to avoid confusion. So what we can see here is that was your alkene. Let me just remove the numbering. So we go from alkene to haloalkane. So we have done something. We have done something to add across a carbon-carbon double bond. And what we have added was HCl, hydrogen chloride. So this is an addition reaction. The type of reaction is addition, but the thing that was asked in the question was the mechanism. So what is the name of the mechanism for alkene chemistry? It's called electrophilic addition. So now you could draw it in skeletal form, you could draw it in the partially displayed form. So I guess the question did ask us, they give us in display form. Sorry, partially displayed form. So I'm just going to draw this in partially displayed form. Perhaps it will be easier for you to follow what is going on. So I'm just going to add in the HCl now. Now we have a delta plus and a delta minus. These are called dipoles and partial charges. Chlorine is more electronegative than hydrogen, so this carry a delta negative because it's winning the tug of war. It pulls the electron closer to itself there. We want to add the chlorine on position 2. That means we have added the hydrogen on position 1. So this is position 1. So I'm going to use the double bond. From the rich, attack the poor. That is your first step. We don't usually write first. I'm just writing it down so you can see which one is the first step. And then you break that covalent bond. That is your second step. And having done that, you are going to get a carbocation intermediate so that you can lose that. And I want the products. I want the product where the hydrogen has now added onto the carbon number 1. And now I will get a plus charge because I have kicked out a Cl minus. So this is now Cl minus. It has a lone pair. In fact, it has more than one lone pair, but we just show the one lone pair because from the lone pair, rich attack the carbon with the positive charge. It doesn't attack the positive charge, it attacks the carbon with the positive charge. Rich attack poor as you form the carbon-chlorine bond, and you will get the final product where you have, oh, that looks a bit complicated, oops, where you're gonna have that. You have added the H on the other end just now. And then now you have a chlorine there because you've already added the H on the terminal carbons. And now you have this carbocation intermediate. This is called carbocation intermediate. Specifically, this is a secondary carbocation because the carbon with a positive charge is bonded to two other carbons. It's called secondary carbocation intermediate. From the nucleophile rich attack poor, you're going to form the final product, which is going to be Q. Outline the mechanism. The mechanism is called electrophilic addition. I've just explained the formation of the carbocation intermediate. So from the intermediate forming the product, overall it's an addition reaction where two molecules have combined together to give you one single product there. And that's it for that 5 marks. For the second part, you're converting Q into R. It uses NH3. So this one is Q into R. So that is the formation of the primary amine. And that on its own is actually a nucleophilic substitution reaction, nucleophilic substitution mechanism. So I've drawn using the partially display formula just now. So you can see that if I have ammonia, to balance this equation, I actually need 2 ammonia, and it will make more sense in the mechanism that I'm about to show you in this case study. So the mechanism is going to be called nucleophilic substitution mechanism. So nucleophilic substitution. So in any mechanism, it's rich attack poor. So let me just try and draw this using skeletal. I drew the previous one using displayed. So there's delta positive and there's delta negative. So the chlorine is the electronegative atoms. And now you have ammonia. Ammonia has the lone pair on the nitrogen, rich attack poor. So that is your first step. And then you will break the carbon-chlorine bond. That is your second step. So how do I know that I proceed via this? I think you only learned this one mechanism in your AQA for the substitution of a haloalkane. And what you get is going to be that. And then you have formed NH with 4 covalent bonds because these are the original NH3. You have formed a dative covalent, or what you call coordinate bonding, such that the nitrogen has a positive charge. You have kicked out a Cl minus. However, it is the other NH3, the second NH3. So this is a second NH3 as a base. What is a base? It accepts H+, is a proton donor, whereas this first NH3 as a nucleophile, it attacks the carbon with the delta plus charge there. So what does the base do? The base will attack a H+, so there's a third step there, and then it will give back the lone pair onto the nitrogen. So from the covalent bond, giving back 2 electrons to the nitrogen, and just like that, it will have formed the amine product. So that is your primary amine, because the nitrogen of the amine is bonded to one other carbon. What did you form? You have formed the ammonium ion, which is again another dative covalent bond, as you use the lone pair to attack and accept a H+ dative covalent bond, tetrahedral shape. There was under shape of molecule, shape of ions. And this is your final ionic salt, because in the presence of a base, the HCl that you might potentially get will form the salt anyway. So this is the primary amine product for this overall nucleophilic substitution mechanism, and it's a reaction between haloalkanes and concentrated ammonia in ethanol, and then you get this primary amine there. For that 5 marks and 5 marks, 2 questions that are worth quite a lot of marks there. What about the next part of the questions? Type of reaction shown by reaction 3. So if you recall correctly, it was that going to the primary amine. So state the type of reaction. So they don't want the mechanism, they want the type. So that is substitution. Identify the reagent. So answer each and every part. You need it to be ammonia. But then the last part, what is the condition necessary? You just need 1. So typically, we would do this in concentrated. So you need concentrated ammonia, because ammonia is a gas, right? So you have to dissolve in a little bit of water. But our main solvent is not actually water. It's going to be in ethanol. So dissolve the NH3 in ethanol, because the NH3 can also form hydrogen bond with ethanol, so they are equally soluble in ethanol there for the condition that is necessary. In part E, the last part of this question, HBr could also be used. So HBr can be made by reacting NABr with corn phosphoric acid. So you don't use concentrated sulfuric acid. So we know that corn sulfuric acid can make the HBr, but there is redox, follow-up redox activity. You should read up on your AS Group 7 halogen chemistry, because you are not just forming the HBr, you are going to further oxidize the Br in HBr to become Br2, which is no longer HBr. Write an equation. So this is just going to remain an acid-base reaction. So this is acting as an acid, this is acting like a base. So what happens is you get the HBr, and then you can potentially just get Na plus and then H2PO4, because you are just giving away one H plus to the Br minus. Or if you don't like this particular format, you can choose to take away all the 3 H plus, then you're going to get Na3PO4, formation of salt, replace the H plus with another metal cations. Of course, we need to balance the equations, 3 NABr, 3 HBr, both are actually correct there. Now identify 2 toxic gases when you have NABr reacting with H2SO4. So we know that there is redox reaction in a follow-up step after the first acid-base reaction together with HBr. So that means no HBr, or they can think of it as except HBr. What else do you produce? You produce SO2 gas and also Br2 gas. It's supposed to be a liquid, but because of the exothermicity, it's very releases a large amount of energy, and Br2 being a simple covalent molecule, quite volatile, it can vaporize to give you a reddish brown fumes. State the role of the sulfuric acid in the formation of these 2 toxic gases. These are concentrated sulfuric acid. It acted as an oxidizing agent. Now in terms of group 7 halogen chemistry, we know about the oxidizing power of the halogen because they are oxidizing agent. They themselves like to be reduced. They themselves like to gain electrons. And that reactivity become less reactive going down group 7 because it becomes less likely to gain electrons. Now what happens is concentrated sulfuric acid lies in between the oxidizing power of chlorine and bromine. So that means this one will not oxidize chloride to chlorine, but corn sulfuric acid can oxidize bromide, which is present in HBr, hydrogen bromide, to Br2 bromine, and hence you can get Br2 gas courtesy of this redox reaction there. That's it for that 19 marks, pretty long question there. I'll leave it for this short tutorial. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do share the channel widely with others, relatives, chat group, juniors, seniors, and friends. And yeah, do get in touch for private tutoring if interested, where I can go through any concepts or any questions of your choice there. Thank you for watching again. I'll see you in the next tutorial video.